Okay, temperature. The temperature of a substance is a measure of its thermal energy. Thermal energy is the movement of the particles. So the particles are in constant random motion, just like people sitting in desks, students in desks. None of you are completely still unless you're dead, right? We're not talking about dead people here. You're breathing, even if you hold your breath, your heart is still beating. There's still some little tiny movement going on. So the thermal energy is a measure of that movement. It's a type of kinetic energy, but instead of moving through space, you're just going back and forth within the same space. So the hotter an object is, the more random motion the particles have, and the higher the temperature. So an analogy to help you remember this is to think about barefoot people on a beach. I live in Reedley. I don't go there very often, but I go to Reedley very often. There's a place called Reedley Beach. Did you know Reedley has a beach? We do. It's actually a very nice beach. I drive by it a lot, and I don't usually stop, but it's a big sandy beach on the Kings River. And of course, later in the summer, it gets much bigger, and this spring, there was no beach because it was all flooded with water. But you think about hot sand in the Central Valley. You're walking from your car, you're trying to get to the river, you're barefoot. Are you going to just stroll through that hot sand? No. There's actually a term for what you do. It's called hot-footing it, right? Because your feet are hot, so you take really quick steps and you get to the river where the water's nice and cold. People go to Reedley Beach because of the cold water. If you go to Pismo on the Central Coast, why do Central Californians go to Pismo in the summer? To get cold, right? People in the rest of the country don't understand this. Most people go to the beach because they want to lay in the sun and soak up some rays. And I go to Pismo because I want to sit in my chair wearing a jacket and covered in towels and freezing when it's 105 here at home, right? So the sand at Pismo is not hot. You can just stroll along. So think of cool sand, walking barefoot. You're just moving slowly. The sand's really hot. You're going to move very quickly. So hot things have a lot of motion in them. The particles are moving. And in a cold object, the particles are moving much less, okay? So heat and temperature are related to each other, but they are not the same thing. Heat is a transfer or an exchange of thermal energy caused by a temperature difference. So temperature is the measure of the thermal energy of the matter. Heat is the transfer of that thermal energy from one object to another. The thermal energy always flows from the warmer object to the colder object. So you have, I left my Rockstar in my car yesterday all day, and I went out and I was just going to pour it over the ice, and I picked up the can, I almost burned my hand. It was so hot from sitting in the car, right? So if you take that really hot Rockstar and you pour it on ice, is the Rockstar going to get hotter and the ice colder? No. The thermal energy from the hot drink is going to flow into the cold ice, and that will continue until they're both at the same temperature, and then the heat transfer stops. So heat is transfer of thermal energy, and temperature is a measure of how much thermal energy there is in matter. Heat has units of energy. So when you're measuring heat, you're using energy units. When we measure temperature, we use a temperature scale. There are 3 different commonly used temperature scales. The Fahrenheit scale is what we're accustomed to in our everyday lives. You know, if you're supposed to bake something at 350 degrees, that's 350 degrees Fahrenheit. If they say it's going to be 97 degrees outside, they mean Fahrenheit. If they ask you what your temperature is at the doctor, all of that kind of stuff we do in Fahrenheit. In science, we use the Celsius scale and the Kelvin scale. And these are metric scales in that they're based on factors of 10. So Fahrenheit is based on the boiling point of water is 212, the freezing point of water is 32 degrees Fahrenheit. Those are seemingly random numbers. There are historical reasons why it ended up being that way. We don't need to know about that, but if you're curious, it's there. The difference here is 180 degrees between boiling water and freezing water. The Celsius scale is based on the boiling point and the freezing point of water. So the freezing point, the temperature at which water freezes or melts, is set at 0 degrees Celsius. And pure water boils at 100 degrees Celsius. And then they just took the difference in there and divided it into 100 degrees. The Kelvin scale is similar, but it's offset. The difference is that instead of water freezing being the 0 point, the 0 is a condition called absolute zero. That is the lowest temperature possible. That would be the temperature at which all movement ceases. All the atoms and molecules in a substance at 0 degrees Celsius would be completely motionless, no movement at all. Any questions? So converting between these temperature scales is something we need to be able to do. And this is something that does require an equation. Because of the relationships between these different scales, we can't use dimensional analysis to convert between them. So here are the relationships. If you have a temperature in Celsius and you need the Kelvin temperature, you take the Celsius temperature and you add 273.15. When we go back and look at the relationship between these temperatures, when we define 0 Kelvin, looks a lot like OK, but it's 0 Kelvin. When we define 0 Kelvin as absolute zero, and we use the same size, a Celsius degree and a Kelvin, it's just a Kelvin, not a Kelvin degree. They are the same unit size, they're just offset from each other. We find that water freezes at 273.15, and so that's where that conversion comes from. Converting between Fahrenheit and Celsius, we not only have to deal with different 0 points, but also the sizes of the degrees are different. And so the equation for that is you take the Fahrenheit temperature and subtract 32, that accounts for the difference in 0, and you take that quantity and divide by 1.8, and that accounts for the differences in the size of the degree. I will give you these equations on an exam, okay? But you need to be able to use them. So let's use them. Convert 350 Kelvin to Celsius. So temperature conversion, got to use an equation. So the equation here is Kelvin equals degrees Celsius plus 273.15. So here I'm given Kelvin and I'm asked to find Celsius. So I need to rearrange this equation. So one way to do that is I need to move this 273 away so I get degrees Celsius by itself. I'm adding it, so if I do the opposite and subtract it, it'll go away. So I subtract 273 from that side. So degrees Celsius plus 273.15 minus 273.15 is equal to just degrees Celsius. This is an equality, and so I have to do the same thing to both sides. So I also need to subtract 273.15 from the other side. And I always make this very awkward. So I have the Celsius temperature is equal to the Kelvin temperature minus 273. Now some of you can rearrange that in your head. That's fine, you do that. So I'm going to plug my Kelvin temperature in, 358, and I'm going to subtract 273.15, and I'm going to use my calculator. 358 minus 273.15 My calculator says 84.85 degrees Celsius. What about significant figures? So this one has 2 decimal places. How about this one? No decimal places. This is a measurement. It's a whole number, but it's not an exact number. So if we're subtracting, we need to go with the one with the fewest decimal places, which is this one. So we should round this one off to the nearest ones place and say it's 85 degrees Celsius. I am not going to be super picky with you about sig figs and temperature conversions, but I want you to try. The simplest rule, which is actually better than even considering sig figs, is to look at the temperature that you're starting with. So 358, and ask yourself, in what place is its uncertain digit? This is the uncertain digit, right? It's in the ones place, right? So then I do the calculation, I get my answer, I round it to the same place, the ones place. And that's what we get here, rounding it to the ones place. Let's do another one. Convert 139 degrees Celsius to Fahrenheit. So the equation was degrees Celsius equals degrees Fahrenheit minus 32 divided by 1.8. But I want Fahrenheit. Well, I need to rearrange this equation. So if I multiply both sides by 1.8, so times 1.8 and times 1.8, then the 1.8 cancels with the 1.8 and goes away, right? So I have 1.8 times the temperature in Celsius now is equal to the temperature in Fahrenheit minus 32. To move the 32 away, to get rid of it, I'm going to add 32 to that side, which gives me just degrees Fahrenheit. If I do it to one side of the equation, I have to do the same thing to the other side. It's like dealing with twin boys. You know, if you give this one a cookie, you got to give the other one the same size, same kind cookie, right? It's got to be equal. So we add 32 to the other side also. And so this side, bless you, ends up being 1.8 times the temperature in Celsius plus 32 is equal to the temperature in Fahrenheit. So now we have our rearranged equation. The Fahrenheit temperature equals 1.8 times the Celsius temperature, 139 plus 32. So 1.8 times 139 plus 32. My calculator tells me 282.2, and I'd put the unit degrees Fahrenheit on that. Anybody else get that answer? So this relationship with the Fahrenheit and the Celsius involves adding or subtracting and multiplying or dividing, and so following sig fig rules gets messy and tedious. We don't actually need to even think about it, because since the Celsius degree and the Fahrenheit degree are very similar in size, we can just keep the precision the same and not worry about it. And so that goes back to what I told you on the previous slide. Look at the temperature that you're starting with. Here it's 139 degrees Celsius. Which of those digits is the uncertain digit? The 9. It's the last significant figure. What place is that 9 in? It's in the ones place. That means I should round my answer to the ones place, to the same number of decimal places as the one I started with. So here I want to round to the nearest one, so that's going to be 282 degrees Fahrenheit. Any questions? What if we need to go between Fahrenheit and Kelvin? Convert minus 321 Fahrenheit to kelvins. There's not an equation for that. What do? We have to use both of them. We have to take the Fahrenheit and convert it to Celsius, and then take that Celsius and convert it to kelvins. So degrees Celsius equal degrees Fahrenheit minus 32 divided by 1.8. Well, the good news is that the equation is set up correctly. We don't have to rearrange that. We can just plug our temperature in. So we've got negative 321 minus 32, that quantity divided by 1.8. Be careful. People miscommunicate with their calculators a lot. You can actually, on most calculators, just type it in as written and you'll be okay. Use the parentheses. So open parentheses and go a negative 321 and subtract 32 and then close the parentheses and divide by 1.8 and press the equal sign. And I'm getting minus 196.111, and it just goes on forever with the ones. So if this was my final answer, where should I round that number? To the ones place, because this temperature was to the nearest one. So I would round it here. I'm not done yet, so I don't want to round it. Do I need to put one repeating for infinity in there to keep my calculation correct? No. Usually carrying 2 extra digits beyond the sig figs will keep you from having any rounding errors. So I can just keep 2 of those and I'll be fine. So that's my temperature in degrees Celsius. Any questions about that? Now I need to take that and convert it to Kelvin. So I need to use the other equation. Kelvin equals the Celsius temperature plus 273.15. So I'm going to take my Celsius temperature. Don't lose the negative sign. 196.11 degrees Celsius plus 273.15. So I still have that minus 196 in my calculator, so I'm just going to add 273.15. And so I get a Kelvin temperature. My calculator says 77.038 repeating, and that would be kelvins. Anybody else get that number? So how should I round this? To the nearest ones place. It doesn't matter if you're going to Celsius or you're going on to Kelvin. Whatever you start with at the beginning of your temperature conversion journey, end with the same number of decimal places. So we should round this to 77 Kelvin. Any questions? If you ever do a calculation where you get negative Kelvin, you did something wrong. You can't have negative Kelvin.